Yes, some work that came out last year with Jakob Moritz, Richard Nally, and Andreas Schachner, and building on a series of other works by us and others, and some work in progress. And let me start with a pretty general overview of what we're trying to accomplish. So the maximal goal of this line of work is to try to understand cosmology in quantum gravity, real 3+1 dimensional cosmology in full quantum gravity, and find solutions of string theory that describe, in broad terms, our universe, that look something like our universe. Now, the issue that sort of comes to the forefront when you try to handle any kind of question in cosmology is the cosmological constant problem, that the vacuum energy is 10 to the minus 120 in natural units. And I will not be able to offer a solution to this problem today, but we're going to go after it in the usual way by defining an easier problem. So the easier problem is a supersymmetric version of the cosmological constant problem. What if we could try to explain vacuum energy being negative in a supersymmetric world, but exponentially small in magnitude? Maybe that would give us some insights about the real and harder problem. Remember that de Sitter space is incompatible with any supersymmetry, but anti-de Sitter space can, of course, be supersymmetric. So what we're going to try and do is see if we can explain how exponentially large but supersymmetric universes can arise in a theory that has a small fundamental length scale, the string scale. And once we succeed at that, we're going to try to use the supersymmetric solutions as a foundation for constructing necessarily non-supersymmetric de Sitter vacua of string theory. So the current goal, then, not the maximal goal, the current goal is more restricted. Let's construct de Sitter vacua of string theory. And we're going to try to do this in totally explicit compactifications with errors that we can quantify. And if we succeed, we'll be constructing fully realized toy models of 3+1 dimensional cosmology in quantum gravity. Now, we won't get all the way to this goal, but we have done something. What we've done is we've constructed candidate. I'll explain throughout the talk what work the word candidate is doing. We've constructed candidate de Sitter vacua, that is to say de Sitter space solutions of string theory. These are 3+1 dimensional de Sitter in Calabi-Yau compactifications, as I'll explain in great detail. So what's shown here is the scalar potential in Planck mass units on this axis in units of 10 to the minus 14 and Planck to the fourth, and this is the volume of the Calabi-Yau threefold in appropriately rescaled units. And what you can notice here is that there's a local minimum of the potential of the purple line that has its value above 0. A local minimum of a potential with positive vacuum energy is a de Sitter solution. Now, further work is required in order to quantify errors from corrections beyond leading order. Now, I should say for those of you who are in the Bootstrap collaboration, I have designed this talk in part for some collaborative work with the string theory community, and I'm going to be proposing certain collaboration goals throughout this talk, which are things that we aspire to do together. So that's what collaboration goal means, something that some of us ought to try to accomplish in the near future. So here's one goal: try to do the further work that's indicated there to quantify errors from corrections beyond leading order. And how do you do that? You actually calculate beyond leading order. So one thing I'd like to be able to do is to compute the four-dimensional EFT that comes out in Calabi-Yau compactifications of string theory, and do that to next to leading order in both the alpha prime and G string expansions. So that's a pretty broad general goal. So in broad summary of the result, what we've done is construct a corner of the landscape of string theory, part of the landscape of flux vacua and Calabi-Yau threefolds, and in that setting, we've explicitly computed the four-dimensional EFT at leading order, including some subleading pieces that I'll tell you about. And in that EFT, we've exhibited metastable vacua. So let me draw a distinction. It's a pretty important distinction. Why am I calling these candidate de Sitter vacua if I'm claiming that I've actually found de Sitter vacua? It's the of the EFT. I've derived an EFT making certain approximations that I think are appropriate and valid, and that EFT has a de Sitter vacuum. Unambiguously, it definitively has a de Sitter vacuum. The question is whether the approximations that I made in deriving the EFT are in fact valid. And that's where the questions come in. So we have to understand whether the EFT I've derived is an extremely good approximation to what results from the full string theory or not, and that will require more string theory work. So saying this in much more detail, but still the same top-level summary, we've computed the 4D EFT and compactifications of type 2b string theory on orientifolds of Calabi-Yau threefold hypersurfaces. And the hypersurfaces are hypersurfaces in certain algebraic varieties called toric varieties that won't play much of a role in this talk. And we've done this at large numbers of moduli in theories with high moduli space dimensions. And we've done it to very high accuracy, as I'll show you. And let me interject here. I understand that this is actually a sort of diverse audience where many of you don't work in this particular subspecialty area. What I'm going to try to do, rather than present everything from first principles in full detail, I know from just having done this at TASI that takes 4 times 75 minutes. So to try and do it here, I'm going to attempt to black box certain things and at least invoke the various notions and then say a little bit about the pieces that lend themselves to explanation. Okay. But you should interrupt if you want definitions of anything, because I can say more. So what we actually do, and this is what the purpose of the talk is to explain, is we find flux vacua with small superpotential by solving a Diophantine problem in the flux quanta. Okay, so I don't expect that that sentence is familiar, but I'm going to explain its content. And by so doing, the complex structure moduli end up being stabilized near a conifold. That turns out to mean that there will be a Klebanov-Strassler-like geometry in the compactification. Then the leading order EFT that's obtained by incorporating in that setting certain instanton effects, Euclidean D3 branes and worldsheet instantons, as well as incorporating the effects of supersymmetry breaking from an anti-D3 brane, has a de Sitter vacuum. And I'll show you. Now, whether these are de Sitter vacuum of string theory, as I've noted, depends on alpha prime and G string corrections to the effective theory. So that's more or less the end of the overview. Any questions before we launch into some things? Okay, plan. First, I'll say a little bit more generally what the context is. How do people go about compactifying string theory in general, and what are the rules, and how do we approach the problem? Then I'll describe one mechanism for getting a small superpotential and hence a small scale of SUSY breaking. In other words, it's a mechanism for a hierarchy. And then at the end, I'll talk about de Sitter vacua. Okay, so if you take type 2b string theory, which has 32 supercharges in 10 dimensions, you compactify it on a Calabi-Yau threefold, called a threefold X, that yields a 4D theory with n equals 2 supersymmetry that has some number of vector multiplets and some number of hypermultiplets counted by the Hodge numbers of the threefold. Now, n equals 2 theory like that has an exact moduli space. And an exact moduli space is totally incompatible with cosmology, in particular with Big Bang nucleosynthesis. You can destroy the light element abundances. It's also ruled out by fifth force bounds. So we know we don't live in a world that has a large exact moduli space. But instead of considering a vacuum solution, a solution with no stress energy with just the geometry of a Calabi-Yau threefold, if you consider a non-vacuum solution with stress energy from field strengths, namely fluxes of various p forms, and as well, D branes and O planes, that non-vacuum solution ends up having less supersymmetry, n equals 1 or n equals 0, and generally not an exact moduli space. I mean, what do you expect? You break supersymmetry and the moduli spaces get lifted, and in general, a whole manifold moduli space will get lifted to a set of points. Moduli stabilization consists of calculating the theory well enough that you can find what those points are, look at them, and find that the Hessian for the moduli fields there is a positive matrix. Then you've found an isolated minimum of the potential, you found a vacuum. So we're in search of vacua. We would like vacua where the Hessian is positive, of definition, and the value of the potential is positive. That's a de Sitter vacuum. So the game really is just to compute the scalar potential in some corner of string theory well enough that we can find places where the scalar potential is positive in a local minimum. That's it. Now you're going to see me doing all sorts of very specific and seemingly contorted things, and it's all governed by our own limitations. We build vacua where we know what the EFT is, and if we had better knowledge of the EFT, we would build vacua in more natural places. That will probably become evident throughout the talk. Yes, please.
Just a basic question, I don't know much. This de Sitter vacuum, like, is it a definition? Is that how you define de Sitter vacuum, that the potential is positive at this critical point, or is it more than that?
Yeah, good. Okay, so, right. So if you find a four-dimensional scalar field theory coupled to GR that has a potential energy function that has a local minimum, then you can automatically, by taking initial conditions, fields at that minimum, and no time derivatives, and metric take a maximally symmetric ansatz, you immediately find a de Sitter solution. So this is a theory that admits such a solution. You could, of course, study things that are time dependent in the same theory, but this is the necessary and sufficient condition for having such a vacuum. Thank you for asking. Other questions? Okay. Okay, so we want to compute the potential in flux compactifications. This involves computing a lot of different specific things. So we need to compute the flux potential by doing so-called period integrals. We have to integrate a certain form over various cycles. These end up being glorified contour integrals, as I'll show you. We need to compute worldsheet instanton corrections. It turns out totally insufficient to work at leading order in alpha prime. We need to include a whole series of exponential corrections in the alpha prime expansion. And we need to compute superpotential terms that come from certain d-brane instantons. I'll explain these in turn. Once you've done that, you then need to try to minimize the scalar potential that results and see if it has, in fact, a positive value at a local minimum. Now, I should say, how interesting is this if it turns out that there are subleading corrections that take away the vacua that we found? Well, in that case, what we've done is sort of pull back one layer and expose a little bit more of the structure of the landscape, and by computing stuff to NLO or NNLO, you'll eventually make your way toward finding the actual vacua, the real solutions of string theory. So we're doing that step by step. Okay, so let's be concrete about the data of an n=1 supersymmetric theory. So such a theory is characterized by two functions: the superpotential, which is a holomorphic function of the moduli fields, and a Kähler potential, which is a real analytic function of the moduli fields. And the important distinction is that the superpotential is protected by non-renormalization theorems. And so in principle, if you're strong enough at what turns out to be computational topology, you can compute the superpotential, and we'll make use of that. On the other hand, the Kähler potential has not been reduced to a math problem at this point. Knowledge of the Kähler potential is a physics problem that's involved in basically trying to understand string perturbation theory in complicated backgrounds. So it's poorly understood beyond one loop. So, yes, please.
Is it important to know the Kähler potential beyond one loop?
Yeah, let's talk about that. Exactly. So what is the general structure is, because of non-renormalization, the superpotential doesn't have a perturbative piece, no polynomial piece. It has a tree-level piece and a non-perturbative piece, and we will know both of these things, I will show you. So we easily compute both to the necessary accuracy. The Kähler potential, the tree-level piece comes sort of from ancient lore, immediately emerges. And then the perturbative corrections, there are some things that are known at one loop. Non-perturbative is completely hopeless. And the perturbative is all orders, right? And now, why would you think you ought to know it? Well, the scalar potential is determined by both. Right, so both enter the scalar potential. So if you had literally no knowledge of the corrections to the Kähler potential, then you would be in a bad situation in terms of understanding the vacuum structure. On the other hand, if you're in a weakly coupled regime, G-string is quite small, and you know all the one-loop data in the Kähler potential, you might be able to argue that you don't need to know two loops. That's certainly the world in which I will try to live. But you should at least know everything at one loop, rather than a scattered selection of one-loop, protected one-loop things, which is more or less where we are now. Is that the nature of the question? Yeah, I am not laying out for you any kind of construction that relies on us being able to get ever more precise, ever higher loop corrections to the Kähler potential. One loop would be sufficient. But in relation to a remark I made previously, all of the gymnastics I'll be going through to find vacua could be avoided if we just knew the Kähler potential to good approximation as some sort of analytic function. Because then the scalar potential would be in hand, and you could just go look and try and find its local minima. Instead, what we're going to do is try and find vacua where our knowledge of the Kähler potential is sufficient, namely at weak coupling. And weak coupling is tough. It's hard to make, it's good for control, and it's hard to find enough structure to stabilize things.
The dilettante is one of the moduli, is that right?
Absolutely, yes. Yeah, the dilettante is, unlike in, for example, the heterotic string, the dilettante will not be one of the hard to stabilize moduli here. The dilettante in this setting shows up in a hypermultiplet, but it gets mass from fluxes at tree level, because the tree level superpotential will, as I'll show you in a few slides, involve the dilettante, and so as soon as you've specified flux quanta, the dilettante gets a relatively high mass. It's the Kähler moduli that end up being sort of the last slippery thing. But yes, we'll have to take care of the dilettante for sure. Okay, so our strategy. What's our basic idea is to use as much supersymmetry as possible for as long as possible, and we're going to choose a setting where, to the extent that it's consistent to do so, the vacuum structure is not affected by the Kähler potential. It's dominated by superpotential terms. Superpotential terms set by integer data. That is to say, set by topology and quantized fluxes. And what we have done already is develop computational geometry software in order to obtain the superpotential, at least, systematically by combinatorial operations that are very fast. And finally, the last piece of the strategy is we're going to use exponentials. Sort of an obvious strategy if you're trying to achieve hierarchies, get small vacuum energy. We're going to find cases where a bunch of competing exponentials lead to well-controlled ADS and DS vacua. That's the game. Okay. Now, why is this happening now? The Calabi-Yau threefold examples that you could get your hands on with pencil and paper are just too limited for de Sitter constructions along the lines I'm going to describe. KKLT here stands for Kachra, Kalash, Linde, and Trivedi. They laid out a blueprint for how you might make de Sitter vacua more than 20 years ago. The Calabi-Yau, this sentence could be modified. The Calabi-Yau threefold examples accessible with pen and paper are just too simple for any kind of de Sitter vacua, in my opinion. And why is that? Because as Busso and Polchinski taught us, in the complicated flux landscape, the discrete dials are the flux quanta. That's what allows there to be a huge landscape. And so you need those dials to have many settings in order for the landscape to have a lot of richness and structure. And so that means you need many moduli. Once you need many moduli, you need to do all of your computations in a high-dimensional setting. And in practice, computational geometry of Calabi-Yau threefolds has advanced enough that the many moduli cases are in reach. So we've been doing this for some time, more than 10 years now, and we can compute the EFTs in Calabi-Yau compactifications in general cases with many moduli, and we can find minima of the potential. I'll tell you very little about that. I'll sketch a few of the more interesting things. I'll show some pictures of it. But what's driving all of this behind the scenes is the machinery for doing toric geometry in a combinatorial way on a large scale on a computer. But we can just pack that away. And you could take this as they learned how to compute the EFTs in Calabi-Yau compactifications, and they started to do things with that data. Okay, so let me tell you about one concrete computation that maybe is a possible illustration of the sort of stuff one needs to do. So a basic piece of data for a Calabi-Yau threefold is the set of integrals of the holomorphic 3-0 form, right? This is the 3-0 form that characterizes the Calabi-Yau, and if you integrate the 3-0 form over a basis of 3 cycles, you get a collection of complex numbers, the so-called periods. And the periods form natural coordinates on the moduli space, and the prepotential can be expressed in terms of them. Since we have n equals 2 supersymmetry, that's all the structure you need. You know the EFT pretty well if you can compute the period. So that's nice. If you could just do this one integral, integrate the 3-0 form, you would know an awful lot of the structure of the theory. Now, long, long ago, it was shown how to do this computation for hypersurfaces in principle. And in fact, Clem wrote a package called Instanton that implements it, but it implements it in cases with a very small number of moduli. And our contribution in this line of work is to develop an extended implementation and a new set of ideas and algorithms that can handle Calabi-Yau threefolds with many moduli. So how many is many? Well, the largest number of moduli, largest number of one type of moduli, Kähler moduli, let's say, in a Calabi-Yau threefold is 491, and we can handle that case now. So the largest known Calabi-Yau threefolds can be handled. And what do I mean by handle? What do you want to even do? Well, if you've computed the periods, then you may recall from mirror symmetry that the data of the periods can be converted to the data of Gromov-Witten or Gopakumar-Vafa invariance on the other side. In other words, integer invariance. And here I just illustrate what we can currently do. This is the number of moduli, so the dimension of the moduli space, the degree of the curve that we compute, so how many multiples of a basic fundamental curve we go out to, how many points we had to sample, how many non-zero integer invariants we had, and how long it took to do the computation in hours, seconds, days, or minutes, not months, minutes. And here's an example in some case where that has 2 moduli, where just for fun we went out to some stupidly high degree to make sure that we could compute these invariants as far as we wanted. I'll show you later why we needed to be able to do this kind of thing and be able to do it at scale. It's essentially because the vacuum structure is controlled by worldsheet instantons, and the Gopakumar-Vafa invariants, like this one shown here, are the prefactors of the instanton terms. So the whole instanton series has a collection of prefactors that are some integers, and you need to compute them. And so we did. So this is just an example of the kind of stuff you have to start computing if you want to get serious about finding vacua in this setting. Okay, enough about the computation. Now let me say the most perhaps important part about the structure of the theory. I'm going to describe the field content. So what are the fields in type 2 compactifications? So if you take type 2B string theory and put it on a Calabi-Yau orientifold, the moduli are the following. There's the axiodilaton, so e to the minus phi, e to the phi is G string. And then there are H21 complex structure moduli that control the sizes of 3 cycles, and H11 Kähler moduli that control the sizes of 2 cycles and 4 cycles. Now, I'm going to work in string units, 2 pi squared alpha prime equals 1. And if I take some quantized fluxes, remember that the type 2B theory has an NS2 form and an RR2 form, and they have associated field strengths, F3 and H3 in RR and NS ordering. And if I choose to consider a vacuum that doesn't have all of the field strengths set to 0, but has some non-zero integer values for the quantized fluxes, then if I define an integer, a combination of these quantized fluxes F minus tau H, so now G, because it's a combination with a complex number coefficient, G itself is not integrally quantized. F3 and H3 are integrally quantized, but then this is a complex linear combination of them. You can write the scalar potential directly from the tree level action in terms of G3. It's basically G3 squared. So this is the scalar potential from flux. And you can take, so this is the sort of component-wise expression for the scalar potential. It's what you get if you just look up the type 2B action in appropriate choice of variables. But you can re-express that in terms of a superpotential. So a superpotential like this. So the Guka-Vafa-Witten flux superpotential is a pairing of the flux with the periods. And what that's saying is if you've selected quantized fluxes and you know where you are in moduli space, then you know what the energy is. Okay, so this then illustrates, I hope, why we would like to be able to compute the periods. Because if you can compute the periods and you can specify a choice of integers for f and h, you know the superpotential and you know the scalar potential. And so we are good at computing the periods, and so we can put that to use.
I just want
Yes,
to,
please.
It's been a while since I've seen this stuff. The axion is the Ramon-Ramon field, or it's the B field with with?
Yeah, very good. Thank you. So C, right, good. So let me, yeah. What is this C0? C0 is the RR0 form. And then you're asking, what about B mu nu and C mu nu with 2 components in space-time and dualizing those? Those are both projected out by the orientifold action. Okay, so yeah, those are in the other half of the hypermultiplets, and they got killed by the orientifold. Yeah, thanks for asking. Right, so the main players here then are the complex structure moduli, which are themselves complex. The Kähler moduli, I should have said, the Kähler moduli here are 4-cycle volumes complexified by the RR4 form. So they're like 4-cycle volume plus I times C4. And then we've got the axiodilaton. Okay, these are the players. And then the superpotential that unites them is this flux superpotential. We like to compute it. But we have to, so we have to connect this a little bit more to the structure of a prepotential. Okay, so now let's lay out the necessary notation to state that. So if I take a basis of H3, as written, and define the periods given by the integrals over the alpha cycles and the beta cycles, then those periods can be expressed in terms of a prepotential. Here the ZAs are the coordinates on the moduli space, and DAF is the derivative of the prepotential with respect to the coordinates. And the structure is as follows. The prepotential near a certain point in moduli space called large complex structure is the sum of a polynomial piece and an instanton piece. Okay, so what's happening here? We're trying to discuss the vector multiplet moduli space. That's a special Kähler manifold. It's characterized by a prepotential. The prepotential is a function of the coordinates z on complex structure moduli space, and we're asking what kind of function is it? And it's a polynomial plus exponentials. And I write out for definiteness what the polynomial part looks like. You don't need to worry about what the coefficients are except that they're topological. So these are intersection numbers, Chern classes, Euler number, just random stuff. But it's just a cubic polynomial in the coordinates z, the complex structure moduli. The instanton piece is some more complicated piece that involves Gopakumar-Vafa invariance and involves some polylogarithms. You should think of it as a worldsheet instanton series with integer prefactors, though. Now, the flux superpotential is, again, the pairing of the periods with the fluxes. And so that means that since the period vector has both polynomial and instantonic parts, the flux superpotential is going to have polynomial and instantonic parts. This is actually very important. The flux superpotential has a polynomial piece and an instanton piece. And our idea is to find a way to choose the fluxes such that the polynomial piece completely disappears. Once the polynomial part of the superpotential is gone, all that's left is exponentials. And if all you're playing with is exponentials, you're bound to find exponentially small things. Okay, so that's all we have to do. Choose fluxes such that the polynomial part of the periods are orthogonal to the fluxes. We'll call such configurations perturbatively flat vacua. They're perturbatively flat because the entire perturbative superpotential is zero by construction, and only non-perturbatively small things matter. So a word to people who are wondering about this, you may say, what's with all the instanton corrections? Isn't this type 2b theory, isn't it classically exact? Yes. This is actually all classically exact, what's shown on this slide. The instantons, the worldsheet instantons, are instantons of type 2a on the mirror. But you can just think of them as ordinary classical geometry in the type 2b side. Yes?
Can you say briefly what is the technique you use to compute these Gopakumar-Vafa invariants, so high degree?
Yeah, very good. So the method is the following. So it's not unrelated to this statement that the prepotential is cubic plus instantons. That comes from a monodromy argument around large complex structure. Once you've sorted out the monodromies around large complex structure and computed the intersection numbers on the mirror, you can use mirror symmetry to relate a computation of the integral. So you can turn a computation of this integral into a computation of GV invariance. So your question was, how do I do the latter thing, or how do I compute the integral?
I think how to do integral, because usually I think of the mirror symmetry as the input, well, it's going from the 2b to 2a, since you're trying to write in the 2b language anyway.
Yeah.
So, I mean, what is the, let's say, the bottleneck of the computation?
In doing the integral?
Yeah.
Yeah, okay, good. So there's a basic, right. So this is the procedure laid out by Hosenow, Clementizen, and Yao is the following. You isolate, so you have a Calabi-Yau threefold hypersurface in a toric variety, and you isolate a particular 3-cycle, and you compute the integral of, you try to compute the integral of omega over that 3-cycle. That period is called the fundamental period. And then there's a sort of a descent system that allows you from that to read off all of the periods. How do you do that one fundamental one? You can reduce that to a contour integral, and the contributions to the contour integral come from poles. The poles come from sites in the cone of curves where there are holomorphic curves with non-zero GV invariance. And so schematically what you do is you first do that integral not for all sigma 3, but for a particular sigma 3 that's preferred by the toric geometry structure. You can write out a closed form expression for that integral, and then you can use some sort of trick for generating complete solutions to the system to map the fundamental solution to the full set of solutions. But all of this needs to be held in line by by using mirror symmetry throughout to make sure that you sort of get the monodromies right and have the structure laid out right.
So it seems like here you have a preferred parameterization of the moduli space in terms of the Kähler moduli of the 2A side of the mirror. Is that important?
A preferred polarization, or
No, just like you know, when you parameterize the moduli, use these the volume of the basic two cycles of the mirror.
Yeah.
Is that important? I mean, because like a priori on the 2B side, naively, I just the simple cases I write down the complex defining equation of the Clapeyron and compute the periods. But here it's important to actually know what the mirror map is.
It's important to know, absolutely, absolutely. It's important to be able to extract. So you might say, why don't you just express the periods as hypergeometric functions? The answer is it's too hard to handle them in that many variables. It's much easier to have a series expansion. And so it's then important to be able to take the hypergeometric data and expand it in a GV series. And for that, we need to be able to relate the sort of the flat coordinates, the ones that appear in the exponentials, to the ones that appear naturally on the moduli space.
And are you always going to be looking for solutions in the sort of relatively large volume regime of the mirror?
Yeah, good. So that's an important point. We are going to be working. So all of this work is around, as noted here, large complex structure, where the prepotential takes this kind of form, and the instantonic part is then a Gokobu-Maravafa series. That we can just use. We have not found the strength to go completely away from this regime, but we can do one other thing, which is we can create conifold singularities as well. So we can approach conifold singularities, but there are other kinds of singularities in the moduli space where we cannot yet compute periods, and that might be a substantial way forward. So right now, what we've done is sort of open the door in the large complex structure realm, but that's all. Okay, great. So our strategy now is to find a way to choose fluxes such that the polynomial part dots to 0 with G. Let me spare you. I'll show you what it looks like so you can see it's not really that involved. You write out a general ansatz for the fluxes in terms of some unspecified either numbers or vectors of numbers. Then you write out what the polynomial superpotential looks like by direct computation, and then you realize that it's not actually that hard to write down an expression for a choice of fluxes that fulfills this condition. Unless someone is curious about it, I will leave it as one slide worth of chasing through equations is enough to get rid of the perturbative piece. When you've gotten rid of the perturbative piece, what remains is the instantonic superpotential. The instantonic superpotential is a function now of just a single variable, and it consists of a sum. Okay, so what is this sum? A sum over curve classes, a flux vector dot a curve class, a GV invariant, which is some integer, and then, well, it's a dilogarithm, but you should think of this as being well approximated by just the exponential inside. So schematically, all of this can be parsed as a sum of exponentials where the prefactors and the exponents are known and computable data. So that's what it all boils down to. Okay. So that's maybe nice. We've been able to line up a computational topology problem where if you can compute intersection numbers and GV invariants, you can compute the superpotential. What do you want to do with that? I said that if you can arrange that you have only exponentials, then you can make sure that the scales come out small in the end. So here's a basic mechanism, a long ago discovered mechanism for doing that, as follows. Suppose you have some superpotential that's a function of one complex variable z. Okay, and suppose it takes the form some prefactor e to the minus an exponent z plus some other prefactor e to the minus some other exponent z. And let's suppose that the two prefactors n1 and n2 have opposite sign. And let's suppose that the exponents p1 and p2 are both positive. So if you think about this as a complex valued function of one complex variable along the real z axis, you can try and minimize it as just an elementary calculus operation. And what you find is the value of the superpotential at the minimum takes this form. So I mean, all I did was differentiate the thing above with respect to z and find the place where the minimum occurs and substitute back in. But the point is that what's appearing here is a ratio to a power. And if this ratio is even a little bit small and the power is sizable, then you have a small number to a big power and you have a huge hierarchy. This is what's known as a racetrack. A racetrack is a situation where you have two competing exponentials where the exponents are close to each other, but they're not exactly the same. So note that if p1 and p2, these two exponents, are very close but not the same, then this quantity here, p2 over the difference, is a big number. And so whatever this ratio is, it's raised to a big number. That's just the fundamental mechanism at play. Now, this is old. What we're going to do is actually implement it. We're going to find cases in string theory where, remember I told you that I could actually compute the prefactors and the exponents. We'll find cases where these will come out such that the resulting value of the superpotential is in fact small. And so let me show you that. So by choosing our fluxes appropriately, we make sure the superpotential is just a sum of exponentials. We can compute the data showing up there, and we can select the ones that give good racetracks. And this now comes back to the point I made very early in the talk about trying to find a mechanism for small vacuum energy in a supersymmetric context. We're engineering integer inputs here. And if you only tweak a few integers and then you get a powerful exponential suppression, that's at least one definition of a natural hierarchy, as in, for example, dimensional transmutation or something. Okay, so let me give you one example of this. So this will be an example that's supersymmetric. So Calabi threefold with 5 complex structure moduli, 113 Kähler moduli. In this setting, we find fluxes, shown here. The numbers, you're not supposed to gain very much from the numbers, except that these are not spectacularly big numbers, some modest integers, such that along a particular direction in the moduli space written there, the polynomial part of the superpotential vanishes. And what remain are the instantonic pieces. The leading ones we compute have GV invariance 2 and 252, shown in red here. And the next one has exponent 43 over 116. And the plus dot dot dot, this is not stuff that I wish I knew. I know all of these. I just don't need to show you because this is already a substantially higher power of e to the minus 1 over g string. And so as long as I know that these ones continue to grow in the exponent, I'm fine. And I do know them. And their prefactors. Remember, I showed you I could compute the GV invariance out to degree 200. So that's not a problem. So now we use it. Well, if you take this superpotential and you just try and ask, well, where in tau is it minimized along the real tau axis? The real I tau axis, sorry. The answer is it's stabilized at g string 0.011, which is a very, very small value of g string. And at that place, the flux superpotential evaluates to 10 to the minus 62. So this is the mechanism at work. Okay, so we were pleased with this. This is a way of getting huge hierarchies from integer inputs at comparatively modest effort in the end. Yes?
Could you remind me how the complex structure moduli turned into tau in the exponents?
Yeah, good, thank you. So the thing that I skipped over because it would have been a slow labor was the following thing. in the polynomial superpotential in principle is a function of the z's, of all of the z's and of tau, and it's some function that depends on some flux data and intersection number data. Now, what we do is we look along a particular direction where z vector is some constant rational p vector times tau. And that's a preferred direction. And it's not the case that the superpotential vanishes everywhere in the moduli space for this choice of fluxes. It only vanishes along a particular valley. Along that particular valley, you can choose, for example, tau to be the coordinate if you want. And so that's what we've done. Yeah, thanks. It's perhaps okay to skip the algebra here, but I should have stressed at least that point. Along that one valley, there's a single coordinate which you can take to be tau. That direction points toward weak coupling and large complex structure. So the parametrically controlled limit in these models is arbitrarily weak string coupling, arbitrarily large complex structure, and all of the exponents go to 0. Great. So in this example then, the vacuum energy in ADS is 10 to the minus 120 with a minus sign. It's negative because it's ADS. Okay. Yes.
Do you ever have to worry about how small if the stabilized modular field gets in the mass that are too small?
Yeah, good. So good point. So this, for example, could not possibly be related to a model of the real world, because when I said that moduli are ruled out because of Big Bang nucleosynthesis, et cetera, these moduli would have mass. Suppose you took this model seriously and asked, well, he's giving me some flux superpotential. He says he's stabilized the complex structure moduli in the dilaton. How heavy are they? The answer is about 10 to the minus 40 electron volts. And so that's way too light for any kind of realism. So that's part of the problem here. Yeah, you would for sure have to worry, and we've made no claims whatsoever that you can do phenomenologically interesting stuff with this example. This example serves to illustrate that there's no conspiracy that excludes exponentially large hierarchies in this setting. Okay. The timer here didn't start, so how much time do I have? 20? Okay, good. So what we've talked about so far, we've talked about all the moduli. I introduced these moduli at the beginning, and so far we've talked about tau and z, but I haven't told you anything about the way that the Kähler moduli show up in the effective theory. They don't show up in the classical superpotential. They show up in a non-perturbative superpotential. And so far we've handled the other guys, so now our task is to make sure that we can also stabilize the Kähler moduli. For this part, I will just sort of sketch what's going on. The general form of the non-perturbative superpotential is the sum of exponentials automatically. And so one just needs to go about computing the exponents and the prefactors, and you're in business. We don't have to go through a labor of getting rid of perturbative pieces and trying to control them. We find Calabi-Yau threefolds in which the superpotential takes a form like this, where the sum is over some set of cycles that I know. The prefactors ADI are some numbers that I do not know, and these coefficients CI are some numbers that I do know, and the TIs are the moduli. And plus negligible means I can actually demonstrate that these are negligible corrections. So the sum runs over some very particular collection of preferred 4 cycles in our geometries. It's not very important. But a point worth stressing here is that the Pfaffian prefactors are constants with no dependence on any of the moduli. They're just some numbers, but they're numbers that I don't know how to calculate. And so we select cases, well, I can skip over the, yeah, please.
So these coefficients A, D, I,
yes.
You say they're constant. Does this follow some non-renormalization theorem?
Yeah, good. So in general, in a general Calabi-Yau threefold, these are Pfaffian prefactors. These are one-loop fluctuation determinants. A fluctuation determinant in general depend on any of the moduli it can get its hands on. They can't depend on the Kähler moduli for a shift symmetry reason, because the Kähler moduli are paired with axions. The axions have a shift, and so only an exponential in the Kähler moduli is permissible in a holomorphic superpotential. But anything else can show up there. Brane positions, tau, z, what have you. What we've done is find cases where the topological precondition for this dependence to be non-trivial is not fulfilled. So it's basically by rejection sampling. We enumerate threefolds and we find conditions under which the dependence is the trivial dependence. So what are these numbers? I don't know. They're somehow some factors of pi times some integer invariant, presumably, but we can't compute the integer invariant currently.
This is some one-loop contribution in string theory or something? Because it doesn't depend on
Yeah, this is a one-loop contribution. The place where I think the one-loop exactness is easiest to understand is the following. Exactly the same kind of superpotential, well, in fact, literally this superpotential arises if you take a stack of D7 branes on a 4-cycle, an engineer Yang-Mills theory, with dual Coxeter number C sub D, because then the gauge coupling function 1 over G squared is T. And so the gaugino condensate superpotential at low energies for a gauge group G, the gaugino condensate superpotential for a gauge group G is this plus a phase part. And that actually corresponds to e to the minus 2 pi t over td over cd, the way I've written it. And now the relation to your remark about one loop is, you may know that in like a totally pure glue theory, you can write down a gaugino condensate superpotential as just e to the minus the Wilsonian gauge coupling function. But in a theory that has some massive states at some high threshold, the gaugino condensate superpotential is instead exponential of minus the Wilsonian gauge coupling function at the tree level, that was the part I was already writing, plus f the Wilsonian gauge coupling function at the one loop level, which is a function of the moduli tau and z. In other words, the one loop threshold correction to the gauge coupling function is the thing that gives this prefactor. And in n equals 1 supersymmetric theories, the gauge coupling function is one loop exact, so that's all there is. So that's why you don't have a whole series of these perturbative corrections. Okay. What did we do to handle this? We basically did our analysis for a wide range of values of these numbers, and the analysis always goes through. They don't matter very much, it turns out. Maybe that's understandable because they're prefactors and the exponents are driving everything. But I would really like to be able to compute them. And in principle, this should be possible. Yes?
Could you explain what is the logic of the duality argument determines that these NDIs are integers but you cannot compute them?
Right. Okay. So the logic. Yeah. Let me be sketchy about this now, and we can get into it in more detail later because I would have to lay out the whole chain. But Moritz has argued quite beautifully that the whole set of constructions that I'm describing is dual to M theory on G2 manifolds without flux, and all of the exponentials that show up here from fluxes and from Euclidean D3 branes are all unified, and they all come from Euclidean M2s. And so it's an integer invariant associated to Euclidean M2 branes in M theory on a G2 manifold. Now, in principle, perhaps computable, but presently not, to the best of my knowledge. Okay. So recapping the supersymmetric theory, we have a superpotential that depends on all the moduli, and we can compute all of its pieces. We chose an orientifold and fluxes that yielded a racetrack PFV that stabilized the moduli, the complex structure moduli, at an exponentially small value of the flux superpotential. We computed the non-perturbative superpotential, and then we need to stabilize the killer moduli as well. I remind you, what I mean by stabilize is once you know what the scalar potential is, just find the minima and exhibit local minima. Here I'll just show you a picture. This is a cross-section of the moduli space. Each polygon herein is one geometric phase. Two adjacent geometric phases sharing a boundary are related by a flop transition. And so this is in a very high-dimensional moduli space, and what you need to do is navigate from some initial point to wherever the vacuum is. And that we can do. So we find a vacuum this way. And what we find are supersymmetric vacua, vacua where the F terms vanish, and ADS supersymmetry is preserved. So that's it for sort of the main structure of the effective theories. And now I can close the talk by talking about how we moved from here to find candidate de Sitter vacuum. We have to add one more thing, which is supersymmetry breaking effects. So how are we going to do that? So Kutcher, Kalash, Linde, and Trivedi made two claims in their famous paper in 2003. They claimed, first of all, in type 2b compactifications, if the flux superpotential is small, then there can exist well-controlled n equals 1 supersymmetric ADS vacuum. That's claim one. Claim two is, if you have such a vacuum in a compactification that also has a warp-deformed conifold region, i.e. also has a Klobanoff-Strassler throat, that contains one or more anti-D3 branes, then claim, in a suitable parameter regime, a well-controlled de Sitter vacuum can arise. So this was the blueprint that they laid out for ADS vacua that are supersymmetric. That's the foundation step. And then on top of that, one adds a supersymmetry breaking effect and finds a de Sitter vacuum. That's a lot. The blueprint has many requisite pieces, and people have written thousands of papers about this, although I will stress that most of the papers about this have been sort of invoking the scenario or thinking about the phenomenology of the scenario, but not trying to do direct calculations therein. But there have been some direct calculations, among which ours. And a fundamental question that we would like to answer is, do there really exist solutions of string theory realizing this idea, or is this just a sketch of something that can only be imagined but not achieved? So the requirements, right? What do they say that you need? They say you need a type 2b compactification with a small superpotential, a warp-deformed conifold, and anti-D3 branes. And, well, in the first part of the talk, I've shown you that we have achieved that first point. We can likewise construct warp-deformed conifold regions, because fluxes cause warping automatically. And we invoked fluxes already to try to stabilize the moduli. And so we just have to be a little bit more enterprising and compute the warp factor. So here I show you the warp factor as a function of position in the internal space in terms of the quanta of fluxes on the non-compact B cycle and the compact A cycle of the deformed conifold. So what I mean by warping here is you have a Calabi-Yau metric in the internal space and some prefactor that depends on the Calabi-Yau metric. And then externally you have, for example, a de Sitter or Minkowski or ADS metric with a Y-dependent factor. So just like in ADS5 cross S5. Bottom line is we can adapt everything that I've told you to engineer warping as well. So this too we've achieved. And finally, we can arrange for the presence of anti-D3 branes. Now, here comes the biggest problem. Main weakness of our whole set of constructions. Controlled supersymmetry breaking, as opposed to just supersymmetry breaking. Controlled supersymmetry breaking from an anti-D3 brane requires that the geometry in which the antibrane is sitting is weakly curved. So you can use supergravity. Weakly curved is parameterized by the flux m, which is the amount of units of RR flux on the 3-sphere, being large. Well, G string m being large, in fact. That just means that it's a nice supergravity throat. And there's an additional condition that the number of flux units should be bigger than 12. Now, you might ask, is he really free to add antibranes? Not really. You can take any compactification you want and add a brane and an antibrane, because that has no net charge. And then if it adds too much energy and you decompactify and destroy your compactification, that's your own fault, but you were free to do it. But you're not necessarily free to add a brane with an antibrane without a brane, or vice versa. There's a Gauss's law constraint, but we check that. And we choose compactifications where the necessary number of antibranes is 1. Okay. Modulo adding brane-antibrane pairs, which is free. Yes?
Could you explain this m greater than 12 condition where this?
Yeah. Good. So this is an old result due to Kotru, Pearson, and Verlinde. And it's not the integer 12. It's actually that 1 over m should be less than a particular real number that's very close to a 12th. Okay, and so what's the calculation? You take some Klebanov-Strassler throat with large flux M, and you put some number of antibranes in it. Then what the antibranes do in the flux background is puff up. They puff up due to the Myers effect. And if the number of antibranes is too large compared to the amount of flux, then they quickly puff up, unwrap themselves, and annihilate against the flux. There's a quick instability. What Katru, Pearson, and Verlinde assessed was, is there a regime of parameters, the size of the throat and the number of antibranes, where instead of being able to puff up completely and annihilate against flux, they form a metastable configuration. And they analyzed that crucially to leading order in alpha prime. And their analysis found that for one antibrane, 12 units of flux is not enough, but 13 is enough.
So this analysis, is it sufficient just to do it in the Klebanov-Strassler, which is non-compact asymptotic conical, or is it important to embed this in the compact lab?
Yeah, very good, very good. So I spent some years of my life studying UV perturbations raining down into Klebanov-Strassler from compactification effects for other reasons related to models of D-brane inflation. And one thing that we did study in the line of papers that I'm quoting here is precisely that effect. So we computed those effects. Those turn out to be small, but it wasn't a priori obvious. The reason you might think it's not an automatic killer is just that the warping tends to hierarchically suppress certain kinds of perturbations, and that turns out to be operative in this case. But we had to do a calculation.
So does the duo for the n=1 gauge theory description Klebanov-Strassler have anything useful to say about this?
Yeah, very good, very good. So this is one of my fondest hopes here, because what you're going to see in a few minutes, I mean, I suppose I have like 3 minutes left or something like that, right? So I'm going to wrap up and show the final construction or the example. What you're going to see is, so we want to get, and I'm going to come around to answering your question, we want to get a set of fluxes and a Calabi-Yau that give. Small flux superpotential, no problem. G string M bigger than 1, okay. M bigger than 12, and number of antibranes equals 1. If we can fulfill all of those, that's exactly what was called for in the original recipe, and then we can assess metastability. What I'm gonna show you is we give a very unsatisfying result here. G string M is not gonna be a lot bigger than 1. And essentially, what's going on is we are attempting to use a collection of tools that we've inherited and that we've built in different ways to find a regime of parameters where a vacuum exists. One of the crucial requirements is the supergravity regime for analyzing an antibrane probing a supergravity solution, because we don't know the alpha prime corrections there. But you say, what if you just tried to study metastable SUSY breaking in the Klebanov-Strassler theory at weak Toft coupling in gauge theory? That would be brilliant. And I don't know of an obstacle other than the inherent difficulty of that problem. I don't know of a physics reason why there shouldn't, in principle, be such a thing. Because what we're talking about here in this whole story is about, so you put an antibrane in Klebanov-Strassler, you're creating a metastable state of that cascading gauge theory. A metastable SUSY breaking state of that theory. And because of human limitations, people have so far discussed this case in the regime where even in the deep IR of the theory after the last cascade, supergravity is still applicable. That's highly non-generic. And it causes no end of difficulties to be forced to do that. And so if only we could understand SUSY breaking in Klebanov-Strassler weak Toft coupling, then I would take away the word candidate from the descriptions of these de Sitter vacua. But yeah, let me show you. So first, a summary of what the basic structures are. We're living off of 3 exponentials. Some of them I've already shown you. First, I showed you exponentials in the fluxes, which we arranged by exponentials in the complex structure moduli, which we arranged by choosing the fluxes. Then exponentials in the Kähler moduli, which come from instantons. They're naturally small. And finally, there's an exponential that comes from exponential warping. Okay, this is, you might think of this as sort of a Randall-Sundrum type effect. They're all exponentials, but they're all different kinds of exponentials, right? These are worldsheet instantons in the mirror. These are Euclidean D3 branes. And this is strong gauge dynamics in a slowly running theory. So just all kinds of different physics, but the mathematics is the same. And you can get a de Sitter vacuum if they all compete with each other. Now, one more remark I have to make about the limitations of our search is the following. If you are just trying to find a supersymmetric vacuum by balancing item 1 against item 2, you have a free dial, which is where the moduli land. And so there's a natural adjustment effect that causes these effects to be comparable in a vacuum without any particular fine-tuning. You know, you have to look, but it works out. If you then try to make a third exponential be of the same size as the first two, you're going to have to choose k and m in just such a way that you hit the right value. And that is brutal because we have to do so-called rejection sampling. We have to make huge numbers of candidate solutions until we find one that has k and m in exactly the right regime. And that's why our search took a long time. Not because we're actually bad at doing each individual calculation. Frankly, after a long time developing it, we're pretty good at doing the calculation one time, but we had to do it 240 million times, and that's what got costly. So what did we do concretely? We found 240 million vacua, and of those, 33,000 have antebrains in the Klebanov-Strassler throat. And let me skip some of the details about the numerical minimization. It's a little tedious to do. It's harder than you think, actually. A lot of the most reputed methods for doing these kinds of minimizations just completely fail because it's lots of teeny tiny exponentials competing against each other in a 300-dimensional space. And so it's a bit of a nightmare, but we can do it. We did it. You zoom in on a target solution, the supersymmetric one, as a starting guess, and then you find the de Sitter one is not that far away. So at the end of all of this, we found 30 vacua. So I show you one, and we'll close. In a certain Calabi-Yau hypersurface with 8 complex structure moduli and 150 Kähler moduli with these fluxes, there's a Klebanov-Strassler throat. And it has one anti-D3 brane in it. And if you include the moduli potential, the way I told you how to compute it, and you include the supersymmetry breaking anti-D3 brane potential at leading order in alpha prime, not including alpha prime corrections to the anti-brane action, then you find a de Sitter vacuum. And the parameters of the vacuum are as follows. M, which remember had to be bigger than 12, is bigger than 12, it's 16. G string is nice and small, W naught is nice and small. G string M had to be bigger than 1, that's bigger than 1, but not impressively so. And the vacuum energy is positive. This is in Planck units. Okay, so what do we make of it? This is the picture of the potential that results. The value of the minimum of the potential is at a positive value. But the question is not whether the potential that I computed has a positive minimum. That's unambiguous. The question is whether I computed the right potential, right? Or are there string corrections that I should have incorporated but didn't? And so if we want to run through like the sort of scorecard, G string is really small. I have no worries about control of the string loop expansion. And this comes back to your point about do we need higher loop Kähler potentials? I sure don't think so. Not at this value of G string. Remember, there's also 16 pi squareds and stuff showing up in loops. Right? The vacuum energy is very small in Planck units. That's very nice. W naught is small. G string M is not large. It's like 1.05. And so the supergravity approximation is an expansion in 1 over G string M, which is about 1. And so it's just totally out of control right now. Now, one can go and compute the leading alpha prime corrections and see if you get a little bit lucky. And that's ongoing work. So in terms of an error budget, we computed the errors we computed the superpotential totally explicitly, so all of the errors are known. The errors in corrections to the Kähler potential and the alpha prime expansion are also known. They only come from truncating huge series at very high degree. The corrections in the string loop expansion, those are only small because G string is small. I actually don't know what the terms are. And the errors in the corrections to the anti-brane action are very dangerous indeed. So what can we do? We can improve our search methods, and we can understand the theory better. So a nice goal for collaboration in this general realm is to try to study corrections to Calabi-Yau flux compactifications next to leading order in alpha prime and G string, including this whole litany of possible corrections. Or alternatively, as I mentioned, find SUSY breaking dynamics in Klebanov-Strassler field theory at weak Toft coupling and dispense with having to use supergravity. So I've told you already what I did. We constructed candidate KKLT de Sitter vacua. We aim to compute alpha prime and G string corrections and search for new vacua that survive in the full string theory. I think because of the technology that we've created, there are now bright prospects, at least in the near future, for systematic construction of de Sitter vacua in this class of compactifications. Thank you.
So I wanted to ask for the anti-D3 brane in the warp reform conical, what alpha prime correction to DBI that you need to know?
Yeah, good. So the leading corrections that are worrisome come from the coupling of the antibrane itself to two bulk curvatures. So it's a curvature, the leading corrections arise at that order. There's a correction from curvature squared, and then there are also corrections from the fluxes. Not all terms involving the fluxes are known to the best of my knowledge, although there's ongoing work on this. The corrections in curvature squared schematically give you something like, and I'll forget the prefactor, but the potential for the antibrane is twice the tension of the antibrane times the warp factor times 1 minus some constant over G string M squared plus ... Where the constant in principle can be determined, that's what comes from the curvature squared, but then these other terms are not necessarily subleading to this one itself, and so it's not that clear whether knowing this constant is that informative. What you'd like to know is all the stuff at low order in curvatures and fluxes.
These are, in principle, just open string tree level things, right?
Yeah. Yeah, it's not inconceivable. It's just that so there's some nice work by the Heidelberg group in a series of papers, Hebecker, Schreier, and Venken in various combinations that took what was, and also that made use of what was in the literature about these corrections, but did not do new string computations. And they analyzed this rather thoroughly in that setting, but I think not yet completely. But if one did just a few more actual string computations, it might settle the issue, yeah.
Other questions for DM? No.
Thank you for the talk. I think you said there was 30 of these that you found with GSM bigger than 1. If you, let's say, ignored that constraint, how many were there?
Yeah, I said that in a misleading way. We found 30 things that had G string of order 1 or a little bit bigger, but some of them had G string like 0.8. If I ignored that constraint, of the 30,000 things, okay, good. So let me skim back to our list of how many things we found. So I thought I had the count here. Yeah, good. Okay, there it is. So the cut down from 240 million to just 33,000 is the requirement that there should be a Klebanov-Strassler throat with M bigger than 12. And that's a big cut. One antibrane, that's a big cut. Now from 30,000 down to 30, it was really two things. One is that G string M is big enough, but in fact, all of these 33,000 had G string M bigger than at least of order 1. If your question is how many more would there be if I allowed G string to be parametrically small, I don't know offhand, but I would guess at least 100-fold more. So, but importantly also, these things are not uniformly distributed in the space of parameters. And some of the nicest places where we would desperately like to be able to do something are the places where G string M is small. There's a very problematic anti-correlation between G string M being small and our ability to control other things. And so even if there were only 30 more in that regime, they'd be way better than these ones.
Thank you.
Well, if there are no more questions, let's thank Liam again.